Combinatorial game theory has several ways of measuring game complexity. This article describes 5 of them: state space complexity, game tree size, decision complexity, game tree complexity, and computational complexity. Measures of game complexity. State space complexity. The state space complexity of a game is the number of legal game positions reachable from the initial position of the game. When this is too hard to calculate, an upper bound can often be computed by including illegal positions or positions that can never arise in the course of a game. Game tree size. The game tree size is the total number of possible games that can be played. The number of leaf nodes in the game tree rooted at the game's initial position. The game tree is typically vastly larger than the state space because the same positions can occur in many games by making moves in a different order. An upper bound for the size of the game tree can sometimes be computed by simplifying the game in a way that only increases the size of the game tree until it becomes tractable. However, for games where the number of moves is not limited, the game tree is infinite. Decision trees. The next 2 measures use the idea of a decision tree. A decision tree is a subtree of the game tree, with each position labeled with player A wins, player B wins, or drawn, if that position can be proved to have that value by examining only other positions in the graph. Decision complexity. Decision complexity of a game is the number of leaf nodes in the smallest decision tree that establishes the value of the initial position. Game tree complexity. The game tree complexity of a game is the number of leaf nodes in the smallest full-width decision tree that establishes the value of the initial position. A full-width tree includes all nodes at each depth. This is an estimate of the number of positions we would have to evaluate in a min-max search to determine the value of the initial position. It's hard even to estimate the game tree complexity, but for some games a reasonable lower bound can be given by raising the game's average branching factor to the power of the number of plays in an average game, or computational complexity. The computational complexity of a game describes the asymptotic difficulty of a game as it grows arbitrarily large, expressed in big O notation or as membership in a complexity class. This concept doesn't apply to particular games, but rather to games that have been generalized so they can be made arbitrarily large, typically by playing them on an n-by-n board. For example, by a lookup table from positions to the best move in each position. The asymptotic complexity is defined by the most efficient algorithm for solving the game. The most common complexity measure is always lower bounded by the logarithm of the asymptotic state space complexity. Since a solution algorithm must work for every possible state of the game, it will be upper bounded by the complexities of each individual algorithm for the family of games. Similar remarks apply to the second most commonly used complexity measure, the amount of space or computer memory used by the computation. It is not obvious that there is any lower bound on the space complexity for a typical game, because the algorithm need not store game states. However, many games of interest are known to be PSPACE hard, and it follows that their space complexity will be lower bounded by the logarithm of the asymptotic state space complexity as well. The depth-first min-max strategy will use computation time proportional to game's tree complexity, since it must explore the whole tree, and an amount of memory polynomial in the logarithm of the tree complexity, since the algorithm must always store one node of the tree at each possible move depth, and the number of nodes at the highest move depth is precisely the tree complexity. Backward induction will use both memory and time proportional to the state space complexity, as it must compute and record the correct move for each possible position. Example: Tic Tac Toe. For Tic Tac Toe, a simple upper bound for the size of the state space is 39 equals 19,683. This count includes many illegal positions, such as a position with 5 crosses and no noughts, or a position in which both players have a row of 3. A more careful count, removing these illegal positions, gives 5,478. And when rotations and reflections of positions are considered identical, there are only 765 essentially different positions. A simple upper bound for the size of the game tree is 9 equals 362,880. This includes illegal games that continue after one side has won. A more careful count gives 255,168 possible games. When rotations and reflections of positions are considered the same, there are only 26,830 possible games. The computational complexity of Tic Tac Toe depends on how it is generalized. A natural generalization is to n(k) games, played on an m by n board, with winner being the first player to get k in a row. It is immediately clear that this game can be solved in DSPACE by searching the entire game tree. This places it in the important complexity class PSPACE. With some more work it can be shown to be PSPACE complete. Complexities of some well-known games. Due to the large size of game complexities, this table gives the ceiling of their logarithm to base 10. All of the following numbers should be considered with caution. Seemingly minor changes to the rules of a game can change the numbers by tremendous factors, which might easily be much greater than the numbers shown.